Okay, this is the last video for Chapter 9, and it covers the third type of bonding, which is covalent bonding. Now, the rest of the course is going to talk even more about covalent bonding. So, in some ways, this is kind of like introduction to covalent bonding. And then, the next chemistry course you take, which is organic chemistry, will be essentially all about covalent bonding. So, covalent bonding is not a little short thing that I can fit in one video. So, I will kind of cover this, especially in contrast to the other two types of bonding. So again, in the ionic bonding, we actually had a transfer of electrons from one to the other, and we had these kind of big ions that attract each other positively and negatively. In metallic bonding, was similar, but the valence electrons there were pooled rather than transferred. In the case of covalent bonding, though, it's a situation where the electrons, instead of them being transferred, are truly shared between atoms. And that sharing of electrons actually forms a covalent bond. So it's almost like the definition of a covalent bond. I'm going to take an example of a really easy, a super basic one to kind of illustrate a few aspects of covalent bonding. So this is in the book too. It's basically hydrogen gas. So hydrogen gas is two hydrogen atoms bonded together, and I'll kind of draw this as H and H, and each of them brings an electron to the party, and they share them. And here we actually have this covalent bond, which is two hydrogen atoms bonded together. I want to illustrate one thing, though, that kind of introduces a couple of concepts, which is, first of all, I've got a graph here started, which on the y-axis here is the potential energy, essentially how much energy in the system, and I'm going to draw that relative to two hydrogen atoms that exist. And then down below here is essentially the distance between the nuclei. So when the hydrogen atoms are very far apart, the energy of the system is zero. There is no potential energy. They don't even know about each other. If you think about it, it doesn't take any energy to push them even further apart, because there is no electrical attraction due to this sharing. But as the atoms are brought closer together, the energy of the system drops. Essentially, kind of like when we're about here, what we have is hydrogen with its electron and a hydrogen with its electron that are sort of close to each other. They haven't bonded, but they're sort of close to each other, where there's an attraction between the left nucleus and the right electron, and the right nucleus and the left electron. They start to form an attraction. And they actually, once they get to a certain point, I'm probably not drawing the inflection totally right, but at about where it inflects, which is right about here, the energy is at minus 432 kilojoules per mole. And at that point, the hydrogen atoms have formed a stable covalent bond. Okay, so they've reached really the lowest energy possible. The two electrons are shared kind of equally between the two atoms, and they've formed a covalent bond. Okay, this length, this distance here, is known as the bond length, or the bond distance. And that bond length is important on a number of characteristics, and you'll see this as we go forward. If you try to push these atoms any closer together, though, the energy starts to go up, and it actually goes up dramatically after that, because once they are, like in this situation, I'm trying to draw it. Imagine that there's two electrons between those two H's. Can you even see that? Here now, the repulsion by the nuclei and even the repulsion by the electrons becomes more significant than the energy drop that was achieved by the electron sharing. So anyway, this graph allows us to kind of see that there is a stable bond length that's formed, and when any two atoms form a covalent bond with each other. All right, let's see what I want to do next. I'm going to follow the book here. Okay, now in the case of covalent bonding, and hydrogen is probably the one exception to this, but in a, I'll erase this. Let's draw a nice little covalent, or a molecule that uses covalent bonding, which is methane. So methane looks like this, also known as CH4. And when we actually do the dot notation, the Lewis dot notation, you'll see that carbon has 4 electrons, and hydrogen each has 1. So in this scenario, carbon ends up with 8 electrons that are shared, 8 valence electrons that are shared. That it either brought or that it is sharing with the 4 hydrogen atoms. And 8, as you probably remember, is kind of a magic number, in that 8 valence electrons will end up taking an atom to its next noble gas. So this arrangement is quite stable, and you'll see in the next chapter we talk quite a bit about valence electrons, and we'll do even more dot structures like this when we get to the next chapter. All right. Now, in each of these cases, I'm drawing them as single bonds, meaning each line that I've drawn here represents a pair of electrons. Okay. Now, what you'll see in some compounds, and I'll draw carbon dioxide, for example. Carbon dioxide, and I've drawn this before, has double bonds, which means that, if you remember, that's what CO2 looked like, which means that carbon has 2 sets of electrons that it shares with one oxygen, and 2 sets of electrons that it shares with the other oxygen atom. And the oxygen, of course, brings in 2 of its own pairs. And so in this situation, if you look at each of the atoms here, carbon has 8 valence electrons surrounding it. It's sharing 4 of them here and 4 of them here. And each oxygen also has 8. It has the 4 that it's sharing plus 2 of its what are called lone pairs. So this is just terminology, but the pairs of electrons are either known as bonding pairs or lone pairs. In this case, you can see each oxygen has 2 lone pairs, and each of them also has 2 bonding pairs. When you have two bonding pairs like this, it's known as a double bond, or a bond order of 2. There are other other bonds as well that you have triple bonds. I mean, nitrogen gas is a classic one. The nitrogen gas has a situation that looks like this, where, hope I got that right. Yeah, each nitrogen brings 5 valence electrons to the picture. So the left one brings these 2 and these 3. And the right one brings these 3 and these 2. So a nitrogen gas molecule has a triple bond, in that it has 3 pairs of bonding electrons. And then each nitrogen atom also has a single lone pair as well. Okay. And what you'll see, and the book talks about this, is that as the bond order increases, meaning from single bonds to double bonds to triple bonds, the strength of the bond increases. And then the other thing to mention here is that and right now I've drawn on the board here, I've got a covalent bond between a carbon and a hydrogen. I've got a single bond, that is. I've got a double bond between a carbon and an oxygen, and I have a triple bond between a nitrogen and a nitrogen. Each of them have different strengths. Some of the strengths are due to the fact that the bond order is higher. So double bonds are typically always going to be stronger than single bonds. And the same thing, triples be higher than double. But also the bond strength will vary according to the atoms involved. There's a really interesting table in your book. It's table 9.2. And what's shown in 9.2 are the typical bond energies, essentially the strength of bonds, according to what atoms are involved in the covalent bond. And it shows, the relative strength. The bigger the number that's shown in the table, the weaker the bond. I know that sounds kind of counterintuitive, but that's the way it is. The bigger the bond energy, listed, the weaker the bond is. Um, uh, yeah. Okay. So let me actually go. I'm gonna take another aspect of this. It's a little bit further. I'm going to talk about bond energies. So, oh, sorry. Before I get into bond energies, how much time? Oh boy, I'm up on time. Maybe I'm going to end this one. I'm going to end this video and I'll start one last one.